Hello everyone, I'm Xinlu from Tsinghua University. Today I will talk about my joint work with Li Jiechen from MIT, inverse exponential correlation bonds and extremely rigid matrices from a new derandomized XOR lemma. In this work, we study the computational power of F2 polynomials. For every integer d, let Pd be the class of F2 polynomials with the degree bounded by d. Every such polynomial can be written as an XOR of many AND terms. Each term involves at most d variables. For a Boolean function f, the correlation between f and the polynomial p is defined as follows. It measures how well the polynomial can approximate the function. We consider the following well-studied question in complexity theory. Can you construct explicit functions that have low correlation with any low-degree polynomial? Given that low-degree polynomials are ubiquitous in both theoretical computer science and mathematics, this problem is clearly interesting in its own right. Moreover, the question of correlation bonds is also very closely connected to the study of AC0 parity circuits, since the seminal work of Rasborov and Smolensky. A partial recent list can also be found below. Now we review some previous work. First, we know that a random function is at most 2 to the minus omega n correlated with sublinear degree polynomials. More than 30 years ago, Rasborov and Smolensky showed that the majority function defined on n bits is at most d over square root n correlated with any degree d polynomial. It is still the strongest correlation bonds known for any functions in NP against log n degree polynomials. For the higher degree, we do not even know a little order 1 correlation bonds for square root n degree polynomials. For d less than little order of log n, there are stronger bonds known. Since there are not much progress for proving correlation bonds for functions in NP, recently people switched to show correlation bonds for functions in larger complexity classes first. So recently, Viola established the function f that is computable in exponential time with access to an NP oracle that is in the class e to the NP. His function is at most n2 epsilon minus 1 correlated with any n2 little order 1 degree polynomial. Independently, Chen and Ren constructed functions in non-deterministic quasi-polynomial time, which are at most inverse super-polynomially correlated with any log n degree polylog n degree polynomial. Most recently, Chen, Liu, and Williams constructed functions in e to the np that are inverse exponentially correlated with n2 half minus epsilon degree polynomials. Now we show our results. First, we significantly improve previous bounds. We construct a function in e to the np that is at most 2 to the minus square root n over log n correlated with any square root n over log n degree polynomials. Here, recall e to the np denotes the class of functions computable in exponential time with access to an np oracle. Second, we show there is a barrier to further improve our results to any constant larger than 1/2, since it would imply new depth 3 AC0 circuit lower bounds, which would be a breakthrough. Third, we also consider polynomials with degree larger than square root n. For this regime, we provide a trade-off result as follows. For every beta in 0 to 1, we construct a function that is at most inverse exponentially correlated with degree n to beta polynomial. We also consider the construction of rigid matrices. A matrix is called rigid if it is far away from any low-rank matrix. Formally, the R-rigidity of a given matrix M is defined as the minimum number of entries one needs to change in M to make its rank bounded by R. Explicit construction of matrices with certain rigidity parameters could imply lower bounds on either arithmetic complexity or communication complexity. We remark that this question is somewhat harder than proving correlation bonds against low-degree polynomials. For an n-bit Boolean function f, we can take its matrix representation M sub f. M sub f is a 2 to the n over 2 by 2 to the n over 2 matrix where M sub f of xy equals f of xy. One can show that if f is low degree, then the matrix representation of f is a low-rank matrix. So if a matrix is far away from being low-rank, then its corresponding function must have low correlation with low-degree polynomials. In the language of circuit complexity, both questions ask one to prove some average case lower bounds against weak computational models. What's known about rigid matrices? First, we know that for a random matrix M with high probability, you need to change nearly half of all entries to make its rank sublinear in N. Second, we know that a random 0, 1 top-list matrix is rigid with certain parameters. These are randomized constructions, and derandomizing them requires exponential time. Third, combinatorial argument can give explicit matrices with such rigidity parameters. We remark that if we want to have rigidity parameter omega n squared, then the combinatorial argument does not give anything non-trivial for rank larger than polylog n. Very recently, based on Ellman-Chen and using tools from probabilistically checkable proofs, Bangel, Harshar, Paradise, and Tao constructed matrix in P to the NP that is omega n squared far away from matrix of almost polynomial rank. We further improved their result by improved rigidity. That is, we construct matrices that keep almost polynomial rank unless you change nearly half of all entries. Note that half n squared is the extreme case, since for every matrix, either the all-zero matrix or the all-one matrix can approximate it on at least half of all entries. In our result, the parameter alpha could be made to be a subconstant, which allows us to strictly improve the result in BHPT. There are two concurrent works by Viola Huang and Lu, which also consider the construction of extremely rigid matrices. They obtained similar results, but with a weaker rank bound than ours. Now let me show you the proof framework. We first review previous results and then discuss the bottleneck of previous approach and our new ingredient. We study an intermediate model, which we call approximate linear sum of circuits. This model has proven to be very useful by several recent work on showing average case lower bounds from algorithmic method. We will talk about them in a few slides. First, fix capital C to be an abstract circuit class or function collection. A function L is called the linear sum of C if it can be written as a linear combination of many capital C circuits. The number of subcapital C circuits is called the sparsity of L. The output of such circuit is in general a real value and not Boolean, but we can still study how well it can approximate Boolean function in the following sense. From now on, we switch the range of Boolean functions from 0, 1 to -1, 1. This is convenient for our purpose, since now we can naturally write the correlation between two Boolean functions as an inner product. We extend the notion of correlation to real-valued functions. For a Boolean function f and a real-valued function L, we define their correlation as their inner product divided by the L4 norm of L. This normalizer factor is required since one can observe that by multiplying L with a constant, the inner product between f and L can be arbitrarily large. This choice of L4 norm is due to certain technical condition posted by the algorithmic method. Unfortunately, we do not have time to explain the details. The linear sum of C circuits is a useful model since it can serve as a bridge to achieve strong average case lower bounds. Let me explain. First, following the seminal work of Williams, we know that one can derive sum of C lower bounds by designing non-trivially fast sharp-set algorithm for capital C circuits. Then, recent work demonstrated that lower bounds against sum of C circuits can be amplified to strong average case lower bounds using the classical approach of hardness amplification. We will explain these two connections in the following slides. Now, first, we explain the first connection and the intuition behind it. In his seminal work, Williams showed a surprising connection between algorithms and lower bounds. That is, a non-trivially fast sharp circuit analysis algorithms for a class of functions could imply lower bounds against that class. Recently, this connection was extended to the sum of C circuits. Namely, if we can design non-trivially fast sharp-set algorithms for capital C, then lower bounds against sum of C circuits follows. Formally, we define the sharp-set problem. We are given a circuit C from a circuit class capital C, and we want to compute the summation of Cx over all inputs x. The intuition behind these lower bounds against sum of C circuits is as follows. A sharp-set algorithm for capital C circuits can naturally induce a sharp-set algorithm for sum of C. Here recall a sum of C circuit L is just the linear combination of several capital C circuits. Hence, we can use linearity of expectation to switch the expectation and the summation. Then apply assumed sharp-set algorithm for each C subcircuit to obtain a fast sharp-set algorithm for sum of C circuit. In general, we have this connection. Let Wn be an increasing function. Then, if we have a 2 to the n over wn time algorithm for capital C sharp set, then we can construct a function in e to the np such that every sum of wn to 1/4 many capital C circuits L is at most 0.99 correlated with the function f in the L4 correlation sense. Now we have established the first connection, which showed lower bounds against sum of C can be obtained from non-trivial algorithms for C. Next, we review how to obtain strong average case lower bounds against C from lower bounds against sum of C. To make it clear, here we use notation capital C sub m to emphasize we are talking about capital C circuits on m-bit inputs. From the first connection, we can construct a function f which cannot be approximated by sum of C circuits. A recent work proved an XOR lemma, showing that XOR independent copies of such a hard function f can amplify the average case hardness. Formally, the new function f2 XOR k, which just receives k independent instances to f and XOR the f value of them together, has at most 0.992k plus wn2 minus omega 1 correlation with any capital C circuit. Note that we are working with range -1, 1 for Boolean functions, so the multiplication is naturally Boolean XOR. Note that this bound decays exponentially fast with k, and it can achieve a minimum of inverse polynomial in Wn. A crucial advantage of this theorem is that it makes minimum assumptions on the circuit class C, namely, we require it to be closed under restrictions and negations, which is satisfied by low-degree F2 polynomials. In contrast, previous hardness amplification theorems usually require the circuit class to be closed under majority. Now we have all the connections we need to prove some interesting results. Using the lower bounds against sum of C circuits as a convenient bridge, we can deduce strong average case lower bounds against C from non-trivial sharp set algorithm for C. We apply the general connection to the case of low-degree F2 polynomials. From a work of Williams, we have a faster than brute force sharp set algorithm for low-degree polynomials. Roughly speaking, when applying to a degree d n-variable polynomial, this algorithm has a 2 to the n over d saving in running time compared to the 2 to the n time brute force algorithm. Then we set parameter d as square root n. We can construct the function f in e to the np such that every sum of 2 to the omega square root n many square root n degree polynomial is at most 0.99 correlated with f. We do the hardness amplification step with parameter k set to square root n. The function g is at most 2 to the minus square root n correlated with square root n degree polynomials. We emphasize that the function g does not achieve our claim due to the blow-up of input length. Note that g has input length n to 3/2, which is considerably larger than that of f. In terms of the new input length L, the correlation bounds and the degree bounds have an exponent 1/3 instead of 1/2. So when doing hardness amplification, the increasing of input length is really expensive. In this work, we save this square root n factor blow up by proving and using a derandomized XOR lemma. Our result is inspired by Impagliazzo's celebrated hardcore sets theorem. We generalized his idea to a non-Boolean case. Let me do a comparison here. We fix f to be a Boolean function. Impagliazzo's result states that if every majority of n over epsilon squared many capital C circuits L, the correlation between L and f is bounded by 0.99. Then there is a set H of size omega 2 to the n such that f restricted to the region H is very hard to predict by capital C circuits. For our case, we start from a weaker assumption. If every sum of n over epsilon squared many capital C circuits has a correlation with f bounded away from 1, then there is a real-valued function h such that for every capital C circuit C, the correlation between f and C and the inner product between h and C are epsilon close. In other words, C cannot distinguish f from h with an epsilon advantage. Also, the function h has L 4/3 norm bounded by 0.99. It might not be clear from this statement that our result is an analog of Impagliazzo's result. So we write his theorem in another form. We define a function hx, which is just f of x times the indicator that x is not in capital H. We can state Impagliazzo's result in this way. we have a function h that is epsilon indistinguishable from f by capital C circuits, and h has L1 known bounded by 0.99. This is because capital H is large. That is, here we view the function h as the mass one wants to subtract from the hard function f to get a hard core. From this perspective, on the right side, f minus h has a similar condition to a hardcore set, but note that f minus h might not be a Boolean function since h may not be a Boolean function. This is why we call our formulation a non-Boolean generalization of hardcore. Hardcore set plays an essential role in derandomizing XOR lemma, and as an application, the derandomized XOR lemma leads to the conditional derandomization of BPP, that is, P equals BPP if E requires exponential circuits. In our case, we use the non-Boolean hardcore to prove a derandomized XOR lemma, and as applications, we obtain the unconditional average case lower bounds as we claimed. To demonstrate the power of our new notion, we present a new proof of the classical XOR lemma. First, we properly define our non-Boolean hardcore notion. Let f be a Boolean function. We call h an epsilon delta witness for f if f is epsilon indistinguishable from h by capital C circuits, and h has L1 known bounded by delta. We remark that having an epsilon delta witness implies a correlation bound as follows. If f has an epsilon delta witness, then f is epsilon indistinguishable from a function that is delta close to O0 function, which means that f is epsilon plus delta indistinguishable from the O0 function, meaning that f has at most epsilon plus delta correlation with capital C circuits. We can now view the classical XOR lemma from a new perspective. The assumption is that every sum of n over epsilon squared many capital C circuits can not correlate with f with larger than 0.99 advantage. Then, using our non-Boolean hardcore lemma, we can construct the function h, which is an epsilon delta witness for f with delta equals to 0.99. To prove our XOR lemma, we show that the parameters of the witness h for the hard function f can be easily amplified to a witness for f2 XOR k. Formally, we define f2 XOR k as the product of f of x1 up to f of xk, where x1 up to xk are k-independent instances. We also define h2 XOR k analogously. Showing h2 XOR k is a good witness is equivalent to prove the following two claims. Claim 1, the L1 norm of h2 XOR k is bounded by 0.992 k. This is straightforward. Claim 2, f2 XOR k and h2 XOR k are order epsilon indistinguishable by capital C circuits. This is the harder part. To begin with, we write the correlation between f2 XOR k and C as an expectation in this form. Then, for every fixed x2 up to xk, we consider the inner expectation. We highlight some terms in the expectation with red color. We call it d of x1. This defines an n-bit circuit that cannot distinguish between f and h, and illustrated in the following figure. Since x2 up to xk are fixed, the circuit D is just the restriction with a possibly negation of the circuit C. So the assumed indistinguishability between f and h applies. We can replace the f of x1 term with h over x1 by a cost of epsilon. So in summary, initially we are dealing with the expectation of fx1 times fx2 times fxk times cx. By paying a cost of epsilon, we switch to the expectation of hx1 times f of x2 times up to f of xk times cx. We can do a hybrid argument and continue this process. For the second expectation, we can fix all but the second instance x2 and do a similar argument. Then, by paying a cost of 0.99 times epsilon, we can replace f of x2 with h of x2 and switch to the third expectation. We do this again and again until we reach to the final expectation, the inner product between h2 XOR k and c. One can easily verify that the total cost we pay is bounded by 100 times epsilon. This completes the proof. So to summarize, we have shown h2 XOR k is an order epsilon 0.992k witness for f2 XOR k, and this implies a strong correlation bounds for f2 XOR k. Now let us derandomize the previous XOR lemma. The idea is simple. We try to design a pseudo-random instances generator G, which generates k instances from a shorter seed of length s, If we have such a generator, we can define the derandomized hard function f_Deran and the composition of f2 XOR k and g. Similarly, we can also define the derandomized witness function h_Deran. Now, the most technical part of the proof is to design a generator G with a linear length seed, such that h_Deran is a sufficiently good witness for f_Deran. To achieve this, we need to prove these two claims, claim 1' and claim 2'. We first remark that claim 1' can be established using several standard techniques in an involved way. For this talk, we will omit the details of the part. We focus on the second part, where lies our main technical innovation. Here, we want to prove an indistinguishability bound. The goal is, for brevity, we let xi be the ith instance generated by the generator G on the seed R. Then the goal is to start from the correlation between f_Deran and C, pay a cost of epsilon to omega 1, and arrive at the correlation between h_Deran and C. We will consider a very simple class of generators. That is, we design G as simply a projection, which means that each output bit depends on at most one input bit. Here is an example. For the given seed R, we split it into 4 parts. We map the first 2 parts to the instance x1, the middle 2 parts to x2, and the last 2 parts to x3. Inspired by the previous proof of the classical XOR lemma, it suffices to consider a single step where we have such an expectation. I-1 instances take h value, then the other instances take f value. And we want to argue it is very close to another expectation where we replace the f of xi term by an h of xi term. In a first attempt, we try to mimic the proof of the classical XOR lemma. That is, we fix all but the ith instance denoted by x minus I. Then we define a function d which computes the red part in the expectation. Then we use the assumed indistinguishability between f and h to argue that we can replace f of xi with h of xi. Unfortunately, this attempt fails badly. Since all of the key instances are generated from a common short seed, we cannot fix all but one particular instance. Therefore, the function d is even not well defined. You can also check the example in the right figure. You can easily see that when fixing x1 and x3, the seed R is totally determined and x2 is fixed also. Still, it is possible that we can fix a part of the seed. Namely, we fix all but the bits that project to xi, which we denote as r minus I. In this example, when dealing with the x2, r minus I is just the origin part of the seed. Now, the function d to r minus I of xi is well defined. To apply the indistinguishability between f and h, there are still 2 challenges to be resolved. First, we want to put d in the circuit class C. To achieve this, we need to carefully design the projection to reduce the dependency between different instances. Otherwise, computing d could be as hard as computing the function f itself, and the indistinguishability bound does not apply. Second, the product of h of x1 up to h of xi minus 1 depend on xi. The product is not a Boolean value, so the function d does not compute a Boolean function in general. This issue turns out to be extremely challenging. Due to time limit, I cannot go into the details here. But the key insight to address this is to use the fact that h has a bounded L4/3 norm, and this implies h has small values on most inputs. Our proof crucially exploits the fact. Okay, to conclude, we prove new correlation bounds against F2 polynomials in class e to the np, and we show it is hard to further improve our results. We also give new construction of extremely rigid matrices in class p to the np. To achieve this, we use an algorithmic method framework with our new technical ingredient. Namely, we develop a new notion called no-Boolean hardcore set and prove a derandomized XOR lemma based on it. Our result generalizes classical work by Impagliazzo and Wiggerson. Our derandomized XOR lemma could also be useful in other applications. It has a much weaker assumption than previous hardness amplification theorems. We only need lower bounds against linear sum of circuits. In contrast, previous hardness amplification theorems usually require lower bounds against the majority of circuits, which is hard to establish. Thank you for your attention.